where. But all right, so we're going to talk about section 2.3 histograms. First thing, visual tool is what a histogram is. It's and to analyze the shape of the distribution of the data. Okay, so that histogram is going to help us kind of visualize what's happening, and we can describe the shape. So it's going to help us to determine if something's like a normal distribution, and if it looks pretty close to a normal distribution, then we can make certain assumptions later on, and it allows us to do certain tests and certain things if it's normal. If it's not normal, then we've got to figure out what else it is. So the histogram built off a frequency table is the basis of making some of those decisions and knowing which direction to go as far as what we're doing with their stuff. Histogram, sometimes confused with a bar graph because they look almost the same. Equal width drawn, adjacent to one another, unless there are gaps in the data. If there are gaps in the data, then what is one of the things that we need to look for if there are gaps in the data? Kind of back into different what? What's that called? Populations. Could be different populations, which is different sets of data. So populations could have more than one of those in there. So when we're drawing a histogram, our bars are going to have equal width, and they're right up against one another, adjacent to one another, and unless there are gaps in the data. The horizontal scale represents the classes of quantitative data. So classes are going to be the x-axis, and then frequency is going to be on the y-axis when we look at the histogram. Okay, heights of the bars correspond to those frequency values. So it's the histogram, the same histogram you did in 6th grade for your science fair project. You made a histogram. How many times you could turn a light bulb on and off before it blew? That sort of thing. Simple like that. So building a frequency table first, and then building a histogram off of that. That histogram is going to allow us to determine if something might be a normal distribution or some other type based on the shape of that histogram and how the bars kind of fill out for us. Okay, so again, horizontal is classes, vertical axis, the y-axis is the frequency values. That's a histogram. Okay. Give me a chance to write some of that stuff down. A little more of we looked at frequency tables last week, talking about those, and we look at the numbers and kind of decide if something was kind of normal out of that. But the histogram is just a visual tool for that, for doing that, and creating a histogram is always good for if it's close to normal but it's not quite that sort of thing. We can see that in the histogram more so than we can just looking at the numbers. Okay. Here's an example of a good histogram and a frequency table that goes with it. So they're using that consistently, using this IQ score stuff here. So they've got a frequency table. They've got the classes here from 50 to 69, 70 to 89. What is the class width for that frequency? 20. Now, how do you find that again? 70 minus 50. Okay. And then what would be the class boundaries? What's the lower class boundary for this, for the first one? 49.5. The lower class boundary for that one, 69.5. Keep going from there, okay? What would be the class midpoint for the first class? How do you get that? Okay, so 70 plus 50 divided by 2. That's the class midpoint. That's going to be important when we go to put it on the calculator. Got to know class midpoint for the calculator, and then we've got to know our class width as well. Okay, so being able to find those things are important for being able to build this histogram. Okay, so again, a histogram is basically it's the graph of the frequency distribution. we're going to see you generating that using technology. Okay, so there's let's go back to that example there, and let's look at the graphing calculator and how to create. We want to create this histogram with our graphing calculator because we may need to be able to do that. Okay, so I want to show you how to do that. All right, so graphing calculator in hand. We're dealing with the IQ scores and that fun stuff. So when we need to go to stat button, which is this button right here beside the circle. It says stat on it. Okay. We want to edit. Before we do that, let's make sure everybody's is set up the same way. So I want to hit 5 and hit enter, and that will reset everybody's list in case some of your lists may have for some reason disappeared or something. So everybody should have the same thing now. You don't have to do that every time. Okay, just do that once. All right, stat, we're going to edit, and we should, when we hit enter on edit, we should get this view, right? Everybody there? Okay, list 1 is going to be your class midpoints. Okay, so the class midpoints from that table. So class midpoints, 60, 80, 100, 120, and 140. $60, $80, $100, $120, $140. Class midpoints. That's going to go in L1, list 1. Okay. The frequencies are going to go in L2. All right. So 3, 33, 35, 7, and 1. So in the graphing calculator, so we got 60, 80, 100, 120. List 2, 3, 30. Let's go back. It was a 2. Thank you. Forget you that. I messed up her data. Make sure we get the rest of them right. 2, 33, 35, 7, 1. All right. Thank you. Forget something. All right. All right. 33, 35, 7, 1. Now we want to make the calculator plot that. All right. So to do stat plot, we hit second and y equals. Blue button and the top left button. It should end up here. I'm going to use stat plot 1 for mine. Make sure all of the others are off. We're only going to use stat plot 1. So make sure they say off. If they don't, then hit enter on there and go in and turn it off. Okay. So here we got plot 1. We're going to turn it on. And then on the type, we're going to select the histogram type, which is the third choice there. The histogram looking thing. Okay. List 1 is your X list. So if yours doesn't say L1 right there, the way to get it to say that would be hit second and then the number 1. Your frequency list, we need it to be list 2, and it's very likely that yours doesn't say list 2. To make it say list 2, you're going to hit second and then the number 2. If you had other data that was going on there, you pick whatever list your frequency is in. So if you had another set of data from another population in list 3, a frequency distribution for it, but the classes were the same, you could do a histogram pretty quickly, but it's using list 3 as your frequency. Okay, so X list, class midpoints. List 2 is your frequency distribution, so we want to put L2 for frequency. Then we're going to hit graph. And everybody should see nothing really. Look like that, something like that. You don't really see anything. Well, we did something with statistics, so we need to get our calculator to move into that area of the graph. So we're going to hit zoom, that middle button right here in the top, and then the number 9 for statistics. And it's going to pull us up to what looks something like a histogram, but it's not quite right yet. Okay? So once we've got here, we see this, we want to adjust the width of our bars. How wide are the bars supposed to be? What we just talked about before we looked at one. The same size all the way across, right? And they're all the width of the class width. What's our class width for our frequency distribution? 20. So to do that, we want to hit the window button and change the X scale. X scale, we're going to change to the number 20. And then just hit enter. And then graph again. And I'm going to hit zoom 9 one more time so it'll just kind of center it. Well, excuse me, I don't want to hit zoom 9 again because it changed my scale again. Let me go back and change it. That last one looked a little short, but I guess it's not. There we go. Now, each bar represents a class. If you hit trace, it tells you the value there. Here's our midpoint, 60. Our count is 3. If I press the right arrow key, it jumps to the next one. There's class midpoint of 80. Count of 33, 35, 7, 1. So we can create that histogram and get that with the graphing calculator based on the data we have. But to get a histogram, what do you have to have first? A frequency distribution. A frequency table's got to be there first for that to for us to be able to do that. So if you need to create a histogram with the calculator, list 1 is going to be your class what? Class what? Midpoints. And then list 2 is going to be your frequencies. You need to set the X scale to the class width. Okay, so those are important numbers to know in order to use technology to create your histograms. All right, so let's go back to our presentation. So, all right, we've already seen that. Here is a relative frequency distribution. What's the only difference in how it's constructed? Percentages. The y-axis is a percent, not a count. That's the only difference. So relative frequencies, percentages, regular frequency is counts. Okay, so that's the only difference in those. What should all those percentages add up to be really close to? 100. Okay. Make sure that looking at data. Okay. When you're interpreting your histograms, we're not just creating a histogram and that's it. We do that in elementary school and that's boring. And but we want to understand something about our data. And what we want to understand is if it's a normal distribution, then we're going to see that in the histogram. Okay, the bell-shaped curve, that the frequencies increase on the left side and go up. They're highest in the middle and then the decrease on the right side. It's almost symmetric where you could fold it in the middle and it match up. That's normal distributions. And we can see that easily with the histogram. That's that symmetry idea with that. It's going to roughly mirror. It won't be perfect, but it'll be really close if it's normal. Okay? Be really close. Let's look at an example of that. Here we have that same IQ score one that we had. What shape is this distribution? What's the center? How much variation is in the data? Are there any outliers? Okay, so we look at those and we see, okay, well, there's a lot going on here in the middle. This curve that they've drawn, that's the normal curve. That's what that's supposed to be, to give you a reference to look at, to see if this looks normal out of that. Where's the center of that data? Does it look like it's about at the peak of that curve? Somewhere around here. It's kind of the peak of that curve is more over this bar, right? And there's more people in this bar, right, than there are this one. But most of them are right here in the middle, right? And then we look at, as it goes this way, well, there's some people here, and then there's a few here, and then there's a few here. Is it perfect? No. Is it close? Yeah, it's pretty close. I think if we had more than this number of people, I mean, we got there 40, 75, 78 people is all we got is data. If we had 780 people, we might see that kind of smooth out a little bit more and be closer. The bigger our number for our sample, we only pick 78 people. That's kind of a small number. We pick 780, the size of this school. I think we get a little better, smoother graph going on there. What can happen is you can have normal distributions and we can have skewed distributions. Normal are going to be that symmetric looking graph. Most of your data is in the middle. And then it trickles out about the same on each side. Skewed data is not symmetric. You can't fold it in half and it match up, or even get close to matching up, okay? Skewed to the right is positively skewed. It'll have a longer right tail, okay? Skewed to the left is negatively skewed, and it has a longer left tail. And I think we've got pictures of that. Skewed right, it's got a long right tail, so this would be an example of skewed to the right. Right skewed, your data might look like this. That's right. Left skewed, your data's got a long left tail, like that. Where a normal is it sits perfectly in the middle and you can fold it. Okay? So skewed right, positively skewed is a longer right side tail. So it's the tail, the end of it, the tail of it that tells you what's going on. It's got a long tail on the right, it's called right skewed. It's got a long tail on the left, it's left tail or left skewed. That'll come in handy when we get later on the hypothesis testing, knowing what kind of test you use based on whether it's normal, right skewed, or left skewed. And which end your number of value falls on, okay? Skewed data, it's pushed one way or another, okay? Pushed to the right or pushed to the left, it's right skewed. If the data kind of falls more from the right, it's left skewed. All right, so let's look at these. What about this green one here? What does that look like? Just glancing at it and making a general assumption. It looks pretty normal, right? Because it follows that nice bell-shaped curve. What about the red one? What do each of our bars in our histogram look like? They're about the same, don't they? They're pretty close to the same all the way across. What you would call that is a uniform distribution. If they're all about the same, it's called a uniform distribution. Uniform distribution. And here's an example of a right skewed. It's close to this, but the right tail is longer. The left tail is longer here. More of your data kind of falls to one end. Okay. So uniform distribution, everybody's about the same. And then right skewed, bigger on the left side, it'll have a long tail on the right side. If you're going down the slide, you'll come out the right side. Left skewed, long left tail. Okay. You're able to recognize those. Really easy thing. Just got to get the words right. Don't get them confused. Okay. Assessing normality with the normal quantile plot. Okay, so we're going to use some different things as we go along here. When we're dealing with assessing normality, does it fit the normal curve? If it does, what can we do with it? A normal quantile plot tells us normal distribution. Points are reasonably close to a straight line. Not a normal distribution. Points not reasonably close to a straight line. So we can deal with a normal distribution using this normal quantile plot. We can decide if it's normal or not by how those values fit close to a line. The human eye is really good at finding straight lines. It's not so good at finding curves. Like, you can look at things and decide if they're lined up or not, but it's very hard to decide if that's a 20-degree curve or a 32-degree curve. It's not, your eye's just not built. You're not built that way. Okay, so you're built really well at finding normal things. Okay, normal quantile plots look like this. They're like scatter plots. Okay, so if you're looking at a normal plot, you're given one, and they tell you this is a normal quantile plot, and the data points are there. If they get pretty close to a straight line, then it's a normal distribution. That data for those things came from a normal distribution. If they don't fit real close, bottom left here doesn't look like it got real close, does it? Then it's probably not normal. Bottom right, it's pretty close, but doesn't it look like there's a little bit of a pattern to those numbers? It looks like it's not following a straight line. It looks like it's got kind of like a cubic equation curve or something like that, which kind of makes me lean toward, I'm not sure that that's normal or not. It's close. It's really close. It'd be a hard one to tell. It'd be one Mr. Isbell would avoid on a quiz because it's so hard to tell. You need to call it a normal quantile plot. We'll talk about scatter plots more as we're dealing with individual data points. Normal quantile plots are coming from kind of a different place. You're looking at variation in the data from the mean is really what you're looking at here. What I'll give you a normal quantile plot, and then you compare it. It's kind of what we'll do here, and we'll see this some as we do some problems tomorrow. We'll kind of see how you're going to get presented the normal quantile plots. All right, let's look at the last section. So first, section 3, a lot of information about histograms. Section 4 is graphs that enlighten and graphs that deceive. So we're going to be looking at different types of graphs and kind of how we can approach those and look at them, and either as really good ones or not so good ones. Okay. Other types of graphs besides a histogram, we're going to look at some of the different ones. Our objective in this is to look. There are sometimes a certain kind of graph is better than others. Sometimes a pie graph is really good. Sometimes a histogram is better. Sometimes a bar graph is great. Sometimes a pie graph is better than a bar graph. Sometimes, depending on your data and what you're trying to show. This is important. The graph should be effective in revealing the important characteristics of the data. That's the key. For it to be an enlightening graph, it's got to be effective in revealing the important characteristics of the data. Okay? Suitable graphs reveal the important characteristics of the data. Right. Because it's exactly right. Did y'all hear what Trevor said? That's a great example. A line graph. He said, don't try to use a line graph for cross-sectional study that's one point in time. Because a line graph would make sense that you would use it on something that you're doing what with? analyzing across some amount of time. So like from year 1 to year 12 of your educational career, you'd be, a line graph would be good to follow there. So, if you're just getting data from one point in time, yeah, definitely a line graph's a bad idea. Great example, Trevor. Thank you. All right. Some graphs are bad because they contain errors. Some are bad because they're just, misleading. Okay. Not because they're incorrect or have errors in the data. They're just misleading. Okay. So you got to watch out for misleading graphs. When we look at bad graphs, we're going to try to figure out what makes them misleading. So we're going to have to have a reason. If I ask you the question, is this a misleading graph? And you say yes, well, the obvious question is why. And so we've got to be able to explain why something's misleading. All right, so here we have a scatter plot. Trevor mentioned, can we just call those scatter plots? Well, scatter plots are just like every data point we have, where normal quantile plots are based off of frequency distributions and things. So plot is paired X and Y axis, and we want to determine if there is a relationship with the two variables there. And this data is talking about waist circumference and arm circumference, randomly selected males. The pattern in the data suggests that there is a relationship, because it kind of follows a trend, doesn't it? That down here, if your waist is 70 centimeters, you probably got skinny arms. Okay, and you get up here, arm size, waist size, they're going together, right? And so it looks like there's some sort of trend there. Not sure exactly what it is, but it looks like there is. Okay. Here's another time series graph. Okay, so we have a scatter plot. Tends to make us think there's a relationship, but there's no true, there's nothing there that shows us this is what's happening. Time series, this is that line graph over time that Trevor was mentioning there. And Dow Jones Industrial Average, yeah, data's kind of old. It's definitely swung back up recently and been up and down for the last 10 years or so. So, but over time, stocks track over time is definitely the way to do that. Anytime somebody throws financial things at you, I think track over time is one of the better ways of looking at that, maybe not a pie graph. Dot plots are a lot like histograms, except for the x-axis is not classes. So a dot plot is an individual, each data point plotted on a line. And if there's like here, we can see that like it looks like 95. They put a bunch of dots stacked on top of each other, meaning there's that many 95. So this is like a stem and leaf plot, but in graph sense. Okay, it's a lot like a histogram, but the class width is not your x-axis. It's actually the data points. That's your x-axis. Let's see. Another type of stem and leaf plot. Here we go. There's a stem and leaf plot. The stem is the tens position. The leaf is the ones position. So 5 and then 06 here means 50 and 56 are those two data points. Here that's 70, 72, 73, 74. It's all of those numbers with a 7 in front of them. Okay. So it may have been a while since you did a stem and leaf plot or stem and leaf or stem plots. Stem and leaf plots, what we've always called it. Stem plot is short name for that. Okay. Bar graphs, we are very familiar with bar graphs. We've done those in plenty of circumstances. We know how to read a bar graph. Multiple bar graph has 2 or more sets of bars on those. Those kind of come up sometimes. That's sometimes a good way to compare data. I see a lot of this with some of our testing data for school. They'll put like male, female. You can pick your subgroups, and they'll put the bars beside each other in the different groups, and compare those, or you might be able to compare class of 2018 to the class of 2019 on like the Alpha 2 or something like that. So multiple bar graphs are always, kind of nice sometimes to compare two more data sets. So when you got those gaps in the data, you can do that. Here's an example of that. Here, they've subdivided male and female. What are they measuring here? Medium income, in thousands of dollars across the years from 1950 up to 2010. Notice both are steadily increasing, and the gap between them, wasn't too far here. It seems to be growing a little bit. I don't know. That's pretty close to the same. Yeah. So definitely kind of shows us a trend of unfairness. A Pareto chart. Pareto chart looks like a bar graph, and it's for qualitative data, not quantities. Your x-axis, notice that it's not numbers. That's the difference. A Pareto x-axis are categories like male, female. Here we got family, friends, leisure, work, study, that sort of thing. It's categories, not or nominal data. It's similar to a pie graph. Yeah, Pareto is a bar graph form of a pie graph. That's a great way to think about that. Pareto is a bar graph form of a pie graph. Here's the pie chart right there with it. This same data between these two. Who contributes most to happiness? Family first, then friends, then your work and your study, whatever leisure is. It could be different for everybody. Music and sports would be last there, according to that data. According to this particular study that they did, I'm not sure, how many people they. Here's the thing. You see a chart. Somebody throws a chart at you with no data to go with it. How do you know they didn't just ask 3 people this and get their data from that? You don't know. So when you're, that's part of the idea here. Frequency polygon, we got x-axis is back to being numbers. It's not categorical anymore. And basically this is a histogram, but with a line graph attached to it. Okay. So here we're using our IQ scores, and each point represents the count for that midpoint of the class, or these are lower boundaries of the class that they've plotted on the x-axis, and they're showing a frequency polygon. What you can do with that, there's some calculus applications to this that you could find the area under the polygon curve and get some information based on that. But we won't get into any of the calculus applications of statistics. Wouldn't get into that until like a upper level statistics class. If you were business majors, you'll have a business statistics that would help you do that sort of thing. Here we have a relative frequency polygon. So again, what's relative frequency compared to regular frequency? Percentages. So we're dealing with those here instead of that. And here they got 2 on the same one, so you compare each boundary to the class is the same dot lined up, and where it's at is the relative frequency out of that. So there's a different type. An ogive is how you say that. Ogive is how you say that name. Cumulative frequencies is all it is. It's just cumulative frequencies on a line graph is all it is. And so, but different ways to that. All right, here, let's talk about graphs that deceive. All right, one of the big things with bar graphs and deception is when you have a axis that's not zeroed. Okay, so when you look at this data, look at the graph on the left. It looks like there's a really big difference in a Honda Civic and a Toyota Camry. The Civic's the first bar, the Camry's the last bar. It looks like a huge difference in those two, right? But when you put it on an axis that has a 0, same data. Doesn't look like very much difference, does it? Okay, so here they've used a non-zero axis, and here they started at 30 and went up to 36. Here we started at 0 and went up to 40 because we didn't have any data over 40, right? So they made it look like, oh, the Toyota Camry is really crappy car compared to the Honda Civic, when whatever the highway fuel consumption, the Civic, it's 36. The Camry's at 31. That's not much. The grand scheme of things is not much. Definitely not much between the Chevy Aveo there. You know, when you look at it with a 0 axis, it really makes it obvious that there's not much difference in it in the long run. But if I'm a car manufacturer and I want to do this and I want to sell something to Ricky Kaufman, I think I could get Mr. Kaufman to believe this graph. Doesn't it look like the Honda Civic is much higher than
performs much better?
Yes. See, but over here, that's the deceptive data.
There you go.
What we have here, this is on a 0 axis, and there's not much difference, is there?
No. I just heard, car consumption. I thought I might be able to do these problems, but as I can see,
you can.
I can read the graph.
That's an important thing we're talking about. Read the graph.
Good work.
All right. Thanks, Mr. Kaufman. All right, so we got non-zero axis. Important to look at those. If you get a mailer or you look at an ad in the or watch TV and they do throw these graphs out there, they don't put a 0 axis on there just because it doesn't make them look that much better. Okay, well, be careful of that. All right, pictographs, world's worst graph ever is a pictograph. Okay, in my opinion, they look incredible. Really jaw-dropping graphics in pictographs. They draw an object, and then they draw another object, slightly smaller, and then they can try to compare the size of those objects as this one is this much better. And, you know, it's like, if I draw an airplane, you know, I got an airplane there, right? And then I draw another airplane. Which airplane's better? Well, but it's bigger, right? Can we compare those two? Because, like, let's say that this represents number of passengers in 2005, and this represents number of people taking flights in 2018. Can we compare those two values? No, because we just got a picture of a plane. We don't have any numbers. We don't have even a bar graph that would show us, hey, the number of people flying in 2018 is this much higher than 2005. Okay, so pictographs, very deceptive. They create all these false impressions about data, because if you stretch a picture, you don't know how much they stretched it to make it look that way. Volume, if it's a 3D picture, that's even worse, because if you double the size of a cube, what happens? Let's say a cube is 4 inches by 4 inches. By 4 inches. And if I doubled the length of this side, and I would have to double the length of all of them. What's the volume of this cube? It's 4 times 4 times 4, right? 64 times 4 is 256. Okay? If I double the size of that cube, it's 888. 6, yeah, it's 4 cubes. Sorry, not 4. I did 4 fours, not 3 fours. 64. What's 3 eighths? 8 to the third. How much? 512? But we only doubled the size. Is this double? Just by, doubling. So when they use pictographs, pictographs. Changing the size of something like here, that's not a bad pictograph because it's kind of bar graphish. If that's a word. Bar graphish. Out of that. But here we're dealing with cubes. That last one is only, it's only 23,000 more than the one before it. It looks a lot bigger, right? So pictographs can always be very, very deceiving because the difference, here, this cube here, if we didn't have these numbers here telling us this, we wouldn't be able to tell that. So if I'm putting that data out there and I want it to look like something's better, I just take the numbers off of it and leave my graph the same. Pictograph, 18,000 and 27,000, that's $9,000, right? Can you look at that and say that's $9,000 bigger? No, it's a bar graph. I can. Okay, so pictographs, world's worst. Here we are. We have same data with a bar graph. Isn't that much easier to compare things with? So pictographs can very, very much be deceptive. From small sets of data, 20 values or fewer, we want to use a table instead of a graph. So a very small set, a table is better because then you can look at each individual, you can look at the numbers, because if we don't get over 20 numbers in there, it's not going to be that much to look at, okay? Graphs of data should make the viewer focus on the true nature of the data, not on other elements such as eye-catching and distracting design features. Pictographs. That was a good example of that. Good graphs don't distort the data. So don't distort your data using, pictographs are a big thing. Pie graphs are not always good. Line graphs are not always good. Bar graphs are not always the best. So be careful to pick one that's better than the others. Also, almost all of the ink in a graph should be used for the data, not for other design elements. If I'm in a presentation and I build up this, really beautiful graph that's got, great background colors, like instead of just having a grid behind it, I put this great watermarked image of my company logo back there, and it looks great for the presentation, but doesn't mean anything for the data. No. Okay, so important principles for graphical representations. Those are some pretty good suggestions out of that. All right. So for tomorrow, and if you want to start on it tonight, since we did 2 sections, so that you get to most of it. Page 58, 1 through 20, page 70, 1 through 26 are the problems we're going to be looking at when we're doing our practice for these 2 sections. This and then we'll quiz on Wednesday, and go from there. So that looks like if we quiz on Wednesday, it will likely be that we have a test